did a pramp interview, and the question I got was root of a number, which pretty much is they want you to come up with a guess and check way, not like a non-algebraic way of finding roots within a certain bound of 0.001. So just for example, here I'll go here. So they want you to say, they give you the numbers n and they give you x in a root function. See those two's right there, and they want to figure out get a guess for value b that's 0.001 more or less in between that that would get there. Algebraically, if you save this, b is just pretty much x to the inverse of n, but they don't want to do it that way. This is they want to create an algorithm for guessing, essentially. So the answer would be 1.93 to the third equals 7. And then like 3 to the 2 equals 9. Yeah, you just always want to make sure when you guess, it doesn't have to be perfect the answer, but it has to be within plus or minus this bound. So a way of going at it is with essentially you just want to iterate and just make guesses. And keep on guessing, hopefully you get closer and closer to the answer within the bounds. You don't want to do that iteratively with a step linearly. So a good way of doing it is like a binary search or divide and conquer method. So for example, usually in binary search you have an array, right? And it's sorted, right? So you have some lower elements and then some stuff in the middle and then like your higher elements, right? So taking that kind of line of thinking, what you could do is make a guess for your lower bounds. Like just so you can guess just 1 is your lower bound, and your high could just be x. And what you want to do in binary search is you always just search the median term, and you check if that's higher or lower than what you're looking for. So we'll take the middle ground of this, so like x divided by 1, or x minus 1 divided by 2, and then we plug that in and see what the answer is. And then we want to check if it's within the plus or minus. So you guess. We want to make sure it's in between our bound, which is 0.001. So maybe for an example, I'll do a different color here. Let's do this 7 and 3. So we can start at x will be 7. So I'll just write it out. So it'll just be 1 will be our lower bound, and 7 will be our higher bound, and then the middle between this is just 4, right? Then we plug 4 into, 4 to the third is greater than 7, so we offshoot it. So then what we can do, this 4 is too big of a guess, so now we can make 4 the high bound. So we can, now we're shrinking, now we're working on 1 and 4, and this is 2.5, which is still too big. Our guess is still too big. So then it'll be 1. And you can see, you can keep on shrinking the bounds until you get it. And just say like the guess is too big, so then you could have something like 1.8 and like 2.5. And you keep on shrinking this size, and you're putting pressure on this side until you get an answer of a median that's within the bounds. So yeah, so it's a binary, iterative, recursive search solution to guessing. That makes it fast guessing. So to do this, I just made an accuracy test function that pretty much does the calculation of how far you're off, it returns a plus or minus. Minus how far you're off what the real answer should be. So, because you take the power, because you pretty much we're guessing bases. So our guesses that are based to the exponent minus x. And I'll say if we undershot or overshot and I return a gap. And then we use this gap function within this while loop. If it's less than this bound or greater than the bound, that means we're outside of it. So while outside of it, keep doing it over and over, and we change the parameters. So, and just for some edge cases, if x equals 1, then it's just going to be 1, right? So if this is 1, anything to the anything is just, or 1 to the anything is always going to be 1. And then let's just say if x was, like this was between 0 and 1, then we want to have the lower bound be x and then the higher bound of 1. So, because x is going to be like 0.0, like a half to 1. So, yeah, so essentially, yeah, what we do is the algorithm works. You make your first guess of what the base could be with the low and the high. And you get the median. So it's just the median guess. And then you plug that guess into the accuracy test, see how accurate is that guess. And then you'll get a gap of how far you're off, plus or minus. And if it's while it's outside the bounds, we have to make another guess. Else, if it's within the bounds, then we can just return that guess, what the base is. So then we just want to see if we overshot or undershot. So if gap is positive, that means we overshot it. So we want to shrink our guess. So we're going to make the high, this is essentially what we did here, we're going to make the high value, we're going to turn that into our medium, our guess. So 4 will go to 7. So we're searching 1 through 4. And then we start a new guess up to the guess base and just guess again. And now instead of having 7 in here, we'll have 4 in here. So 1 through 4. But else, if we undershot it, that means the gap is going to be negative. Then we want to raise our guess. So that means when we do this step here, we raise 1 to 1.8, something like that. So we put pressure this way. And then, yep, then you, just redo your test and you get a new gap. And then a gap that's either going to be outside or inside these bounds. And you just keep doing this over and over and over, like this loop. You can see why it's recursive. Well, it's not recursive. Kind of, because it's calling. Well, it's an iterative approach. What am I thinking? You're iteratively updating. Your guess, which is contingent to gap, or gap which is contingent to guess base. And if we print this out, we can see all the steps. So the first guess was like, I thought it's like, all right, how about 2.5 as a base? Oh, that's too big. How about 1.5 or 1 7/5? Nope, that's too small. How about now they did a lower guess than 2.5 and higher. As you can see, it kind of ping pongs back and forth until you get to this, which was within the bound. Yeah, and that's pretty much it. So let's just say we want to do an exponent that's less than 1. So what base to the 5th power will equal 0.85? Let's see how this works. Yep, so this is too small of a bound, so that try a bigger guess. That's too big, too small. I mean, yeah, what's the guess? That's too big, too small, too big, too small, and so on and so forth. So yeah, and that's pretty much kind of how it works. Yeah, it kind of says it has a recursive approach to it. But it was weird for me when I first did this. I had trouble thinking like an iterative recursive approach where you're not calling a function. Well, you are calling a function, I guess. Accuracy test over and over to get a gap of a new guess. Yeah, so it's recursive, and base case will just be if it's within the bound, and then you decrement or increment and decrement on high and low. So this is the recursive function accuracy test, and also you always have to, in recursion you have to have a increment or decrement part of your variables, and guess base is because your low and high are getting updated every time. So, and then the runtime of this, apparently, yeah, it's constant time, since all of the inside work is constant time, and then you eventually will get to your answer ping pong back and forth. So, and the space time is also constant too, because you're keeping a fixed set of non-growing variables in memory. Yeah, it was a pretty fun problem. Let's do something big here. I just want to try something here. So let's do like 1,204 to the 18th. See what this does. Yes, so you can see those are kind of big numbers. I don't know how this was scaled, but yeah. So I'm guessing it's not going to grow too fast, even if you get an absurd amount of variable numbers. So yeah, the first guess is 301, but the guess is, as you can see, you start off as a wildly horrific guess. It's 301, and as you can see, so it kind of halves. So 300 to 150 to 76 is kind of going half and half and half until you get to the bound. So yeah, apparently at 1.483 to the 18th will equal 1,204. Anywho, that's it.